Imagine a world where your smartphone, your car, even planes lose their way, all at once. What could cause such chaos? High above us, beyond the serene blue sky, a tempest brews in the heart of our solar system. This storm isn't made of wind and rain, but of charged particles ejected from the sun in a spectacular display of cosmic power. We call this a severe solar storm. While solar storms are a natural astronomical occurrence, their beauty belies their potential for disruption. Most people know them for creating stunning auroras, often seen in polar regions. However, their impact extends far beyond these light shows. A particularly strong solar storm has the capability to cripple the technology we depend on every day. From navigation systems in our vehicles to timing systems that govern electric grids, solar storms pose a significant threat. Their ability to disturb the Earth's magnetic field can disrupt satellite operations, affecting everything that relies on GPS technology. This isn't science fiction, it's a real threat from our sun, and it targets one of our most relied upon technologies, GPS systems. But what exactly is a solar storm? Imagine the sun, a swirling mass of hot gases and magnetic fields, suddenly releasing a colossal burst of energy. This dramatic spectacle is known as a solar storm. At its core, a solar storm can include two primary phenomena: solar flares and coronal mass ejections. Solar flares are intense bursts of radiation emanating from the release of the magnetic energy associated with sunspots. These flares are the solar system's largest explosive events, and they can last from minutes to hours. They are so powerful that they can actually affect all layers of the solar atmosphere, accelerating particles to near light speed. Moving on, we have coronal mass ejections, or CMEs, which are even more significant. These are huge bubbles of gas threaded with magnetic field lines that are ejected from the sun over several hours. Unlike solar flares, which are more light-based, CMEs are massive physical expulsions of solar material and magnetic fields into space. When these gigantic eruptions happen, they don't just stay around the sun, they travel through space. And this journey brings them into contact with planets, including Earth. As they reach Earth, these charged particles collide with our planet's magnetic field. This interaction can create stunning displays of auroras near the poles, where the magnetic field is strongest. However, the influence of these storms goes beyond just visual splendor. The Earth's magnetic field, an invisible shield protecting us from the harsh solar and cosmic radiation, is susceptible to these solar events. When a particularly strong solar storm hits, it can compress Earth's magnetic field and cause temporary disturbances. This compression can lead to a variety of effects, including disruptions to satellite operations, communication systems, and even power grids. These storms are more than just spectacular light shows. They are powerful enough to disturb the very magnetic field protecting us. From the sun to our smartphones, the journey of a solar storm is a tale of energy unleashed. Imagine a colossal wave of energy born from the chaotic heart of the sun. This wave, known as a solar storm, begins its trek across the 93 million miles that separate us from our star. Traveling at speeds up to 1 million miles per hour, these storms are a flood of charged particles hurtling through space. As this cosmic tempest approaches Earth, it encounters the planet's magnetic field, our first line of defense. This invisible shield, generated by the Earth's rotating core, acts like a force field, deflecting many of the storm's charged particles. However, some manage to penetrate, following the magnetic field lines towards the poles. The energy of these particles cascading down towards Earth doesn't just create the beautiful auroras, it also sets the stage for disruptions in satellite communications, including those crucial for GPS technology. As these storms reach Earth, they begin to interact with all things tech, especially our GPS systems. How does a storm hundreds of thousands of miles away affect your GPS? Let's delve into the ingenious world of Global Positioning System, or GPS, as it's more commonly known. This technology, which many of us take for granted, is a network of about 30 satellites orbiting Earth at an altitude of approximately 12,000 miles. These satellites continuously send signals back to Earth, signals that are picked up by devices in our cars, smartphones, and even watches to determine our exact location, speed, and time. But here's where our story twists. These signals are incredibly delicate and can be disrupted by phenomena far beyond our immediate atmosphere. Enter solar storms. These storms are explosive events on the sun's surface, hurling energetic particles and magnetic fields across space. When these solar emissions, known as coronal mass ejections, make their way to Earth, they can cause dramatic changes in the ionosphere, the layer of Earth's atmosphere that is ionized by solar and cosmic radiation. The ionosphere plays a critical role in the transmission of GPS signals. As the signals traverse the ionosphere, they are bent and slowed, a process that normally GPS systems can adjust for. However, during a solar storm, the ionosphere swells with these extra-charged particles, intensifying these effects and making the ionosphere more turbulent. This turbulence scatters the GPS signals, much like light rays deflected by a prism. The result? A degradation in the accuracy of GPS calculations. This can range from a minor annoyance, like showing you a few meters off your actual position, to more severe disruptions, including complete loss of GPS functionality. For applications that require pinpoint precision, like aviation or military operations, the consequences can be dire. So the next time your GPS glitches, consider this. It might be the echoes of a solar storm. No GPS? More than just an inconvenience, imagine a world where pilots can't navigate, ships are adrift at sea, and ambulances can't find the quickest route to a crisis. This isn't the plot of a dystopian novel, it's the potential reality of a severe GPS disruption. GPS is woven into the very fabric of our modern infrastructure. It's not just about finding the nearest coffee shop, it's a critical tool for high-stakes operations across various sectors. Take aviation, for example. Pilots rely on GPS for en route navigation and for landing, especially in poor visibility conditions. Without it, their ability to safely guide aircraft is severely compromised, potentially leading to delays, diversions, or worse. Moving to the seas, global shipping depends heavily on precise location data to navigate through busy and dangerous waters. A GPS failure could result in massive maritime traffic jams, disrupted global supply chains, and significant economic fallout. On the streets, emergency services use GPS to respond to crises swiftly. Imagine the chaos if GPS data suddenly went dark. Ambulances, fire services, and police could face delays, which in critical situations could mean the difference between life and death. Furthermore, even our financial systems are tied to the precise timing provided by GPS. Transactions and operations could slow or halt, causing financial turbulence and uncertainty. The ripple effects of a GPS outage go far beyond a rerouted road trip. Can we protect ourselves against these celestial onslaughts? As we've seen, solar storms pose a real and potent threat to our global positioning systems, but not all hope is lost. Innovators and scientists are hard at work developing technologies and strategies to shield our skies from these solar tempests. One of the primary defenses against solar disruptions is the enhancement of satellite technology itself. Engineers are designing satellites that can withstand the intense radiation and charged particles unleashed during a solar storm. These robust satellites are equipped with more resilient electronics and thicker shielding, which can help maintain their functionality even when faced with solar flare-ups. Additionally, there's a growing emphasis on predictive models. These advanced algorithms are capable of forecasting solar activity with greater accuracy, providing essential warnings before a storm hits. This early detection allows for crucial adjustments to be made to satellite operations, minimizing potential damage and disruption. Another exciting development is the implementation of redundant systems. By creating networks of satellites that can back each other up, the impact of a few satellites going offline becomes less crippling. This redundancy not only ensures a more stable GPS network, but also secures other critical infrastructures like telecommunications and energy grids. Research into these areas is not just ongoing, it's accelerating. Collaborations across international space agencies and private tech giants are pooling their resources and knowledge to tackle this high-stakes challenge. While we can't stop solar storms, we can certainly prepare for them. Awareness and preparedness are key. As we've explored, the vulnerability of GPS systems to solar storms is not just a theoretical concern, but a pressing reality. Our world, increasingly dependent on precision and timeliness, stands at a crossroads. The technology that guides everything from airplanes to stock transactions could falter under the intense pressure of solar emissions. This underscores the importance of global preparedness. It's not enough for one nation to shield its infrastructure. This is a challenge that crosses borders, demanding a unified approach. International cooperation is essential. By sharing data, strategies, and technological innovations, countries can fortify themselves against these celestial threats. Innovation plays a crucial role here. Developing more resilient technologies and constructing robust protective measures are not optional, they are essential. These advancements are vital in ensuring that our society can withstand the disruptions caused by solar activity. As we continue to reach for the stars, let's not forget the fiery power of our closest star and its impact on our technological world.